Hi, in this video, we want to take a look at classical test theory reliability. All right, so here's the idea. I have, let's say, a test that I give students, and I want to know, is it a good test? All right, I mean, that's a reasonable question. Is it measuring what I want it to measure? All right, well, subject matter knowledge will definitely come into play for me to look at the question, see, hey, is it doing what I want it to do? Yeah, that's going to be important. But we want also a like data-driven way to measure, is this a good test? So if I have a good test, it's going to be reliable. Now, when I say reliable, that means that conceptually it's consistent. What do I mean by consistent? Quite the rabbit hole of this conversation. But consistent means that if I was to go and give the test again, I will get nearly the same results. Okay. So there are tons and tons and tons of ways to measure test reliability. Psychometricians have definitely gone down this rabbit hole and studied this and nuanced it. And if you go online and you start studying up on this, you'll see lots of people arguing over which way is the best way. I'm going to present three different measurements, and these are three that I think are reasonable. They're very common and they're well established. All of them are a good choice. Okay, so the three measurements of reliability that we're going to look at are Cronbachs Alpha, greatest lower bound, and McDonald's omega. All right, Cronbachs Alpha, what it does, it takes a test and treats each question as a test by itself and uses that to establish a relationship with measurement error. Greatest lower bound, okay, so Cronbachs Alpha, if you look at the derivation, it's actually a lower bound to a reliability measurement of the population. All right, well, if it's a lower bound, that means it's not exactly what I'm looking for because it's a lower bound, not an equality. Greatest lower bound, this measurement is an improvement upon the lower bound aspect of Cronbachs Alpha. And then we have McDonald's omega, which uses factor analysis. All right, now, a good question to ask is, which one should I use? Well, first and foremost, you should consider what will your audience accept. All right, so if I'm going to be doing something, let's say I'm going to publish in a journal, an education journal, what previous papers in that journal, what did they use as their measurement of reliability? If you're on a committee or you need to present to a committee, you need to convince decision makers, then you should use whatever their preference is. So if you saw one of them published a paper using a measurement of reliability, you should use that one. And you can produce multiple, by the way. That's always a good idea. My opinion is that I would prefer Cronbachs Alpha because it's well established, it's well known, and it's a known metric. So a lot of people will accept it because it's taught very regularly in the education realm. Now, it's criticized up, down, left, and right, justifiably so, but because it's so well established, I feel like it's the best choice. All right, so let's go ahead and do an example. And here we're running an example from Modern Psychometrics with R. It's in the Use R series of books. And the book has its own package. And if you're doing psychometrics work in R, you're probably going to be using the Psyc package. And for here, this is the R motivation data set. And what we're going to do, we're going to look at only the hybrid columns. And that's just to reduce it down so that I have a little bit, I have fewer things to be looking at. Now, something that's done here in this example is to omit the rows that have missing values in them. Okay, so the NA omit takes the data frame. Any row that has a missing value, it gets kicked out. Now realize that there's, by doing this, I'm really just like washing my hands of missing values, but I'm also missing out on potential information. So this may not be the best choice, but as a first go around to get familiar with these measurements, we probably should not be dicking around with the missing values. All right, so let's go ahead and look at our data. So here we can see that we've got binary data. All of these are hybrid columns. Now, what is it hybrid of? I believe it's motivation for making R packages. All right, so now let's look at our first measurement of reliability. Here is Cronbachs Alpha. All right, Cronbachs Alpha is always between 0 and 1, but we want it to be between 0.8 and 0.9. If it's more than 0.9, then there's probably something hinky going on, that like it's too good to be true. If it's below 0.8, then it's not at the level of reliability that we want. So 0.8 to 0.9 is where we want it to be. Okay, so for now, what we're going to do, we're going to go through and we're going to compute Cronbachs Alpha by hand. So we're going to look at the number of columns that we have in our data set, because remember, Cronbachs Alpha treats each question as a test by itself, and that's how it splits it up to measure this reliability concept. And so here we have 19-ish. I'm not going to go through and count each column, but I've got hybrid 1 through hybrid 19. So it's about 19 columns. And we're going to take the covariance matrix of the data of the zeros and ones. And we're going to take the trace. Now remember, the trace of a covariance matrix is an estimate of the variance. And then and I'm adding it up with the trace. The diagonal would just be the individual variance terms. And then here we have 3.6 for the trace. Now, if I take the sum of the covariances, now remember, covariance can be positive or negative. So some of the off diagonal terms are going to be canceling each other out. But if I have a good solid test, conceptually, like negative covariance would correspond to negative correlation, right? And how often do we see in the realm of human performance on something like a paper and pencil test, would we see negative correlation? It's not going to be very often. So if it's negative, it's probably pretty small. All right, so what we do to get what we want for Cronbachs Alpha, we take the trace of the covariance matrix, we take the sum over the entire covariance matrix, make a ratio. All right, this has to be less than 1. No, it doesn't have to be, but realistically it's going to be. And then here we take 1 minus that. And then we take this ratio of the number of questions divided by the number of questions minus 1. And then in the end, we get 0.82. Okay, so that's on the low end of what we want, but it's in the realm of what we want. If it was, if it broke 0.9, if it's above 0.9, I would start, there's something probably wrong about this. Maybe there was a repeat of a question. Maybe, several questions are asking the same thing, even though I thought otherwise when I wrote the questions. Now, if I look at the square root of the covariance term that we got earlier, and we take the square root of 1 minus Cronbachs Alpha, we get 1.7. All right, now let's go ahead and use the Psyc package to do the calculation for us. So in the Psyc package, the function is called alpha. Very nice. And what we do, we just drop the data set straight in. And it gives it to us very nicely. So here, I take the total, I take the first item, and I'm rounding it to 2 digits, and I see that I got exactly what I worked out a moment ago. Now let's go ahead and dig a little bit deeper. Let's look at the summary. All right, so the raw alpha value is 0.82. Standardized alpha is 0.82, that's good. And then G6, which is another measurement of reliability, is 0.84. The average R, because remember, we've got multiple columns, is 0.2. S over N is 4.6. And then we have these other terms floating around where we have our mean, our standard deviation, and the median R. So now let's look a little bit deeper into this. If I look at what I get from the alpha on the hybrid data, I can see that I have the same thing I just looked at from the summary. Here I get a confidence interval on a 95% confidence interval on my Cronbachs Alpha. And so we can see 0.8 to 0.84. And so the entire confidence interval is within the realm that we want. That's good. And now here, it breaks down for each of the individual questions what's going on. So we see a raw alpha for each question. We see a standardized alpha. And then we get another measurement of reliability. Then the average R. And eventually we get down to the median. Oh, here's our standard error, very important for hypothesis testing. And here are the item statistics themselves. So here we can look to see how did things go for like the mean of the responses and the standard deviation of the responses. And here we can look at the missing values. And so this is very important when students look at a test and they go, oh, I don't know how to do that. I don't understand it. Or that's just a long question. I'll go ahead and skip it. So missing values can tell us a lot about our test. It could just be that the student's not motivated. It could be that the question was poorly written, so the student just skipped it altogether. And so here we get an idea of what's going on. All right, now an alternative estimate to test reliability is greatest lower bound. So if you look at the derivation of Cronbachs Alpha, that's actually a lower bound on the measurement of reliability. Well, it's a lower bound. Could we do better? So we know that the reliability, up to, like issues with measurement, that Cronbachs Alpha is going to be less than or equal to the actual measurement that we're working with up to some statistical aspects. All right, well, could I get a better lower bound? Well, I could get the greatest lower bound. And that's, if you've taken mathematical analysis, you are very familiar with greatest lower bound. And we just do GLB in the Psyc package. And we get some values. We get a beta factor. Here we have alpha PC, GLB max, which we've seen before in our confidence interval. Here we have a factor analysis output. And we get some measurements from psychometrician literature. And here it gives us some details throughout. So what we'll notice is that we get a slightly increased value. I think it's 0.83. Where is it? Oh, so it's giving us a 0.88 for our greatest lower bound, which is not surprising. It has to be greater than or equal to Cronbachs Alpha. Now, another way to get a measurement of reliability is use factor analysis. And this is where this comes into play for McDonald's omega estimates. Okay, and it'll calculate the value. So factor analysis is the idea of there's some like under the hood proficiencies that are driving the output that we see. So here we see like the general factor, and then we have individual factors coming into play. And we can see these numbers give us an indication of the connection between each of the questions and each of the factors. The bigger the number, the greater the connection between the factor and the question. And we can plot, we can do a scatter plot to take a look at the individual questions. And so we can see that they're getting grouped together by shape and color. And if I look here, like the blue looks all scattered between F1, factor 1, factor 2. But when I look at factor 1, factor 3, I can see, oh, yes, it looks very reasonable for these guys to be together. When I look at the red squares for factor 1 and factor 3, it looks like, they're kind of dispersed. But when I look over here, factor 1, factor 2, they look well grouped. And so if you look at this for a little bit, you'll eventually, feel more comfortable with how this works out. All right, now here's the summary of McDonald's omega. And so here we see our alpha, we see our G6, another measurement of reliability. We have 3 different omegas. Now, remember I said previously that psychometricians have nuanced reliability measurement a lot. There are no shortage of ways to measure reliability. Here are 3 that are connected to omega. And here are the eigenvalues connected to the factor analysis. And here we can look through, like we have a p-value that's super small. And here's the root mean squared error of the residuals. Here is our Bayesian information criterion. And this gives us a relationship between each of the factors and these omega terms. All right, well, that's all I've got for you. Take care and goodbye.